Hello, and welcome to Chapter 9 of The Good Earth. This is part of the KBOCC Earth History course. Today we'll be discussing weathering and soils. Table of contents here, as we usually do for this chapter. We'll start with the dirt on weathering. Get it? Video dish, it's funny. Then we'll go into the different types of weathering: physical, chemical, biological, and decay. We'll discuss a bit about rates, and then we'll end the conversation with a talk on soils. Before we get into the soils, I will say soils is not my big thing. It's a super interesting topic, but it's not something I studied a whole lot of when I was in school myself. So I apologize if it's a bit abbreviated. If you have any comments to say on soils or something I missed, perhaps, feel free to leave them in the comment section down below. As usual, any questions or comments, email them, leave me them down below, and let's get into it. So, weathering. Let's look at that picture. Kind of creepy looking, right? What's going on there? I mean, those are pretty tall rocks. Look at the size of the shrubs down there. You're talking, that's not the size of your knee there. And they got very large holes in them. Where could those holes have come from? How did this develop this Swiss cheese-like appearance, like it says there? Well, maybe the title of the chapter will give you a little bit of a hint, right? Weathering. Weathering is the physical, chemical, and biological breakdown of rocks and minerals. Again, breakdown being the key word there because it takes the rock in its pristine condition and it damages and deteriorates it in some way. We can look at these 5 World Heritage sites here: Pantheon, one in Tanzania, Angkor Wat here in Cambodia to the side, right? And we can look at, these are made of rock. These are made of the natural present material that is around there. And I think the Pantheon is a great example of this. They are not in the same condition that they were when they were created. Why is that? Well, nature takes its course, right? Rocks are constantly being affected by the environments that they are present in. So as nature happens to the Pantheon, or as nature happens to Machu Picchu up here, things get slowly destroyed. That's not what Machu Picchu looked like way back in the day, right? Machu Picchu was like a full-on like temple or something like that. Now it looks like that. The Pantheon used to have a complete roof to it. Now it does not. That's what weathering does. And I always say it, whenever we get these tests, I'm not going to go through them. However, if you would like to pause and answer them before you continue, be my guest. All right, soil. Soil is formed by weathering and is often eroded faster than it is replaced. Soil is in dirt, mud, all those things are basically the surrounding rock material. When it's broken, it's busted up in little teeny pieces. Those pieces are what makes up soil. Different soils come from different soil types are in direct relation to the surrounding rock. If you have a clay heavy soil, you probably got a lot of clay rock surrounding you. That's how that works. Here we have an example of a side picture. This is a nice cutout crop showing you the different levels and different amounts of material underneath your feet, right? The vegetation, that material, the grass and stuff like that, that's always just a thin little section of what's below the surface, because you have soils, you have bedrock that comprise a large amount of what's underneath our feet. This picture here showing a good example of that, right? We'll get more into this later, but soil is vast majority still that dirt, right? Like the difference between dirt and soil is, well, you don't grow like plants in dirt, right? You grow plants in soil. Because well, dirt and soil are both primarily mineral fragments and busted up rock, soil also has water, organic materials, airs, important nitrogen, stuff like that, right? Important elements that the plants need to thrive. If you just have regular dirt, this stuff is lacking. Plants don't like to grow in it as much. That's why you buy soil from a gardening store, right? You don't buy dirt from the same place you buy your soil. So that was a little brief on soil and weathering. Let's get into specifics now. Weathering. Physical weathering is the disintegration, the breaking up, the combusting, the destroying of rocks and minerals into smaller pieces. There's a couple terms we use about this, but as with most things in geology, I like to say the way you're picturing it going down is probably the way it's actually happening. So keep that in mind as we go through some technical terms here. First of all, we should talk about unloading. Unloading is the process of erosion stripping away overlying material. Essentially, right, if something happens to the rock, then it's going to happen to the top of the rock first, like rain, for example. Rain's going to happen at the top of the rock. And as the rain hits the top of the rock and removes the top of the rock, the bottom parts of the rock have less pressure on them and they uplift. When they uplift, they can expand and they can create more surface for weathering to continue on. So unloading is one of those, like, you don't think about it, but it's a real cool concept. Like, rocks are constantly moving up as nature affects them, right? They're constantly producing more of themselves to be eroded by just how density and gravity work. Here we have an example of this. A on the left here has a batholith. This is a old extinct volcanic magma chamber. And then as you erode down from the top, eventually the batholith has less pressure from the dirt on top of it. So the batholith is able to move and expand up. As it moves and expands up, you go over to B, right? Those sheet joints, I think we have pictures of those later, so I can explain. There we go, perfect, sheet joints. They're called sheet joints because they kind of look like bed sheets, right? They look like pages from a book. And that actual feature, the reason the feature looks like that is it's the batholith exhaling, it's releasing its pressure. That's what's causing all those breakages to happen. And we see this on a small scale all around us. If it looks like sheets are coming apart, it's literally the expansion of the rock. Now there's no pressure underneath it anymore. It's pretty cool. Let's got a couple more examples here. Pressure cracks, right? Another physical weathering phenomenon we can have is wedging. We talked about this a bit in class so far, but this is the erosion that happens, the weathering that happens when you put something in a crack of someplace. For example, water gets into a crack in a rock, the water freezes. What happens to water when it freezes? It grows, it expands, right? It applies pressure to the rock crack. That's going to push the crack open. It's going to erode and damage the rock. And that's going to disintegrate the original product. Potholes. Everyone knows what potholes are. This is how potholes work. The road itself is not perfectly impenetrable. It's porous to some extent. Water gets down in the road, freezes, turns into ice, pops sections of the road completely out. There you go, right? Exactly what we're looking at here. This wedging can also start a process of other this wedging can start the process of other weathering effects to continue to erode and decay away the remaining rock. If you get some water in a rock, for example, that can wedge and create a hole that will allow larger minerals like salt crystals in. Salt crystals will then grow and expand and further deteriorate the rock. When you see examples of rocks with crystals in them, they kind of look like that little holes that crystals are going inside. That's probably what happened there. Something weathered a hole in the rock. Minerals got into that rock that allowed for crystal growth. As the crystals grow, they continue to pressure and destroy the rock further and further and further. The growth of the crystals is weathering the material. And the more you weather something, the more it breaks down, the more surface you have to weather, and on and on and on. It's a slow starting process and a fast ending process. That's why there's so much dirt everywhere, because it's a lot easier to weather 24 little teeny squares than it is to weather one big square. A lot more surface material on the right. So that was physical weathering. Let's talk chemical weathering. Chemical weathering is the same end result, but via a different process. This, as the name suggests, is the chemical is the result of a chemical interaction within the material. Think dissolution, for example, acid rain, right? If you ever been to a graveyard and seen older gravestones that do not have the detail that the newer ones have, that's not because they're old, it's because they're probably made of a softer material like a marble, for example, that is more susceptible to rain and stuff like that, washing it out. Even better practical examples, chalk. Chalk is a mineral. Chalk is a rock, essentially, right? But you all know, especially if you have kids, chalk melts in the water. So if you make your chalk designs on the sidewalk, rain comes by, washes all that away. That is a chemical process of the chalk being dissolved into the rainwater. It's picked up and it's moved. That's dissolution. That is the exact process that undergoes when you have a chemical reaction resulting in weathering. Hydrolysis is another thing we can get into. This is more of a getting into the molecules section of things. And hydrolysis occurs when the hydrogen ions, H plus, in water replace ions for, say, silicate materials. What does this mean? Well, we have feldspars. Feldspars are the pinks and the whites in a granite rock. It's a good example so you can picture a feldspar. The pinks and the whites in a granite. And these feldspars will react with water and the clay minerals. And clay minerals will actually form within the feldspar, chemically altering the original component, manufacturing a glossy texture to them. And you now have a new product, and the old product is being washed out. So you're losing material via feldspar. The feldspar is dissolving, if you will, but through a different mechanism. Oxidation, that's the gravestone example I told you before. Oxidation, of course, rust, right? It happens to everything. So it happens to every mineral, more or less, except I think for like silver. I don't think silver tarnishes, it doesn't oxidize. But copper, of course, is a good example for us up here on the copper country, right? Now, I don't think I need to explain oxidation. If you have a car, you know what rust is. As an example, right, of this chemical weathering process, wherein this statue did not originally look like this. All those little pits and holes and stuff like that come from the natural process of the rock losing its parts due to that chemical and physical weathering. Here we have a sugar cube dissolving in a cup of coffee example. You probably know what dissolution is. You've put sugar in your tea or coffee before. You notice the sugar and the tea grains don't exist anymore because they get caught up in the liquid. Same process. Here we have a picture on the left of a cave. This is probably going into, costs and caves. Lots of caves throughout the Americas, as this map shows here, are limestone caves. Limestone, of course, is very susceptible to water and erosion. So the holes that were created by these caves, we have gypsum caves as well, the actual removal of the materials was a chemical process when the water got in there and dissolved the limestone via the couple of the mechanisms we talked about previously. And then as the water left, it took essentially the limestone away out of the cave in solution, leaving you these large cavernous environments. Sinkholes, these are the result of processes like this. If you dissolve enough limestone away, the rock on top of the cave collapses in, causing a sinkhole. Hydrolysis, right? It's a variation on the same topic here, wherein you have something, in this case, carbonic acid, for example, coming in, chemically altering the material such that it is no longer attached in the same way. and is able to be removed. Chemical weathering process. Right? Acidic and alkaline materials, right? pH scales, all those sort of things. And again, it's interesting that, you know, you guys have probably all seen, if you've never seen it, watching YouTube, was it like Coca-Cola's effect on the human stomach and all that, and how Coca-Cola is actually very acidic and will actually like you can cook things in Coca-Cola because the chemical reaction breaks down the meat so much. That exact same process will happen with rocks, although it's not longer of a process than, like, you know, hamburger. Rain is mildly acidic. The more acidic it has, the more damage it does. Acid rain is called that for a reason, right? And then, of course, you have your natural acids, your microbial mats and stuff like that, which can do, it's all variations of the same tune here. The important part about the natural acids is these are also a byproduct of human interaction with the environment, such as mining. A lot of minerals are found with acidic host. So a lot of ores, a lot of like metals, you know, irons, coppers, nickels, what have you, are found with acidic host rock. So when you destroy the rock to get the ore, the valuable metals inside, that water is using that process, and the chemical reaction of the host material with the water will actually produce acid. And as you can see from this picture here, that acid comes downstream and more quickly erodes the surrounding environment than you had before. Right. So we've talked about biological weathering and decay a lot in the class labs. This is your plants, your animals, your termites, your biological material causing destruction of the rocks, right? And it's not just the physical action of like tree roots moving or insects burrowing holes, but also the result of them eating things, the animals defecating, let me think for a second here. The dead bodies decomposing. All these things are adding more variety to the rock, more variety to the host material, therefore causing it to decay and these chemical and physical interactions to happen more frequently. So biological weathering, this example right here, this is a physical process the tree is going under. So we describe it as biological based on what the source of the weathering is, but it's having a physical process. Ice wedging and this wedging are pretty much the same thing, right? You have, you know, coal and trilobites and stuff like that, right? Destroying the rock. It's all part of the process that nature undergoes. Here you have the water, of course, is going to come in. It's going to erode out, weather and erode out underneath the rock that we're looking at here. But then you also have the slimes and the plant life and the animal life that's also playing a factor here. Big grand scale conversation about this, be it physical, chemical, biological, all three are always constantly working in sync with each other to erode and move and transport the material, right? The rock, no rock is being broken down exclusively by one of these three mechanisms, unless it's like really deep in the earth or something like that. So we talked a lot about weathering mechanisms. Well, what is weathering? How fast does something weather? Well, the first way to determine how fast something is being weathered is what is it? A softer rock like chalk will weather a lot faster than a harder rock like a granite. And that's simply, right? The words soft and hard are exactly what you're thinking about for that example. Porosity is another example. Here's a concept survey. Pause if you want. Porosity can play another big component. The more easy it is for, say, water to get in, the more easy it is for the water to deposit those minerals, which can then grow and physically alter and push around the host rock and break it apart. Composition, as we said here, is very important. Whether it's faster in rocks composed of weaker materials, such as feldspars and clays and what have you, whether it's faster in rocks that made up of minerals that dissolve in water. If salt is a major component of your rock, you get it wet, salt dissolves in water very easily, right? So you're losing your salt fast. And weathering is slower in rocks made of resistant materials. That's the opposite of step one there. There's a reason why we have so much quartz around, because quartz lasts a long time. You can get very large quartz crystals very easily because the quartz will continue to grow even though the surrounding host rock is weathered away. Weathering is faster in rocks that allow air to flow through. This is the porous thing I talked about before. Fractures, of course, will grow and grow and grow and grow and grow, right? If you look at a tree that's growing out of a rock, you can notice directly underneath all the cracks that the roots have made is dirt everywhere because the tree is physically rubbing the rocks apart and creating all that dirt. And igneous and metamorphic rocks generally have low porosity, which makes them survive around longer. Sedimentary rocks naturally have higher porosity. Picture a sandstone versus a granite, right? Climate, of course, is very important. Chemical weathering is more common in warmer climates. The more rain you have, the more opportunities for the different types of weathering, probably the more active microbial life, the more active plant life and stuff like that as well. And just shade and stuff like that can all play a big factor. There's everything that goes into, say, how a tree can grow will go into how fast that tree can weather away what it's standing on. Carbon dioxide, again, going back to that acid rain conversation we had before. The more freeze-thaw cycles you have, the more ice wedging you have, right? Picture, roads, and also the more rusting oxidization you have. Picture roads up here in the UP versus roads down south where there's less freeze-thaw cycles. Or again, would you rather have a car from Georgia or a car from Michigan? Well, car from Michigan is probably gonna be more likely to get rust on it. Excuse me. Ooh. So here's another picture. Here's another question. Feel free to pause it if you want. And let's go into soil. Soil is the last thing we'll talk about for this chapter. And important key factors here is there's a difference between soil and dirt, and there's a difference between soil in any particular location. Every soil is unique and different and can provide you with many different benefits, right? So we're going to define soil here as a stratified mixture. So it has layers to it, separate layers of regolith. That's a fancy term for soil. That includes enough organic material, water, and air to support plant life. Again, dirt, you don't grow plants in dirt, you grow plants in soil, right? Organic material in a soil tends to be supplied by whatever's died above it, being plant life or animal life. And then as the organic material falls into the dirt, if you will, it gets mixed in, and that mixture is what results in the soil. And then if the soil is porous enough, you can have water sit in it and stuff like that, and we'll work our way through. In general, we refer to what the soil looks like as its profile or its horizon. And then you have different distinct layers or horizons within that soil that do different things. The top part of the soil, we got a picture here. There we go. So pause and read if you want. Pause and read if you want. This works the best using this example here. The very tip top of a soil horizon is what known as the O horizon. That is your very surface layer where the roots are barely going in. You're walking on top of it, right? Below the O layer is the A horizon. This is the topsoil. This is the things you buy from the garden store. This is where most of your shallow roots sit. This is where the carcasses of everything that's died ferment around. This is where you have good porosity so water can get through and sit there very easily. Topsoil is the thing you want. You want good topsoil. High amounts of various minerals that plants like, such as nitrogen, very important. So topsoil is where the money is, right? Deeper the topsoil, deeper the high quality food the roots can pull out of, okay? Below your topsoil, and E sometimes doesn't exist. So in general, though, A, topsoil is always there, otherwise you don't have soil. Your E zone, your E horizon, the zone of leaching, is also very common. This is where you're starting to lose that percentage of organic material and you're getting into whatever the host rock is, right? The part where the water goes through the topsoil and then just kind of goes straight down, but the organics haven't gotten down far enough to hit that zone of leaching. So zone of leaching is your boundary zone between your topsoil and your subsoil. Subsoil is where you really don't have the organic material anymore. You simply have kind of the leftover amount of the mineral, of the rocks and the sediments sitting down there. Your roots will only go down there for like large trees, more as an anchoring point. And again, it's that connection point between the nice fine topsoil at the top and your parent rock, your bedrock, your like rock. Roots don't go down there in your sea horizon. So that is a simplified soil profile, starting with O, which is your grass, essentially. A is your soil. E is a transition zone into your subsoil, which is kind of the topsoil with all the good stuff. And then your C, the very bottom, that's your parent rock. That's rock. You don't have soil anymore. All these sizes and amounts can change. The deeper you get into soils, the more subdivisions you have in here, the more you do. If you want a garden and have it mean something, you need to know what your soil is so you know what's compatible to grow in your soil. I'll say that much. Yeah, soil formation is primarily the result of the rock in your area. If you have a lot of clay, you have clay-rich soil, okay? There's also the temperature and rain components. The more rain you have, the more it can break it up a bit, and maybe you can expand your topsoil down into your zone of leaching because the rain is able to slosh around and bring down the nutrients that you want. And of course, biological activity. That's the reason why we put earthworms in our gardens, right? So here's another question. Cool. And some pictures of types of soil. Soil is very, very varied. And it's worth noting here that some of these maps kind of align, right? You do have, you gotta zoom in on these pictures. It's kind of annoying here, but you do have correlation between biome, between which is sort of the temperature and the weather of the area, with the types of animals that live there, types of vegetation that live there, and the type of soil that's in the location. All these three things are very much connected. Your biome and your biome that produces rainforest will give you soil that's conducive to rainforest, and vice versa. They all feed each other. Soil fertility. This goes back to a couple of things I talked about before. Soil fertility is not simply how thick your soil is, but it's more importantly what's in your soil. You can have thin soil that's very, very nutrient rich, and certain plants that do not have deep roots will love it, right? Or you can have very lots of soil, but if you're missing, your important minerals, if you're missing your biological component, you're going to have an issue here. Example being the rainforest of dense vegetation, but the extreme rainfall carries nutrients away. So you have very, very, very high quality soil that's not super thick. So if you try to plant something like corn there, corn doesn't grow well. You really got to put a lot of effort to get corn to grow in the rainforest because corn wants to go down and rainforest plants wants to go out with their roots. Some of the examples that we're talking about here. Notice the size of the topsoil on the left versus the right, and then how deep the soil part of the soil goes in a temperate climate, because you have more organic material to go down there and mix in, pushing those different horizons down. Right? Let's look at that example here. Don't have a lot of variety. So are we looking more at an arid or a temperate picture here? Consider those things. So here's another checkpoint. Pause if you want and read it. All right. I'm I'm on the news. I switched over to a different Zoom, so I have a lot shorter time. So let me just check. We got a bit to go here. I'm going to pause this video now. I'm going to take it up again in part 2. That way I have enough time to properly go over the last 10, 15 slides and I don't have to rush everything in. So thanks for watching. See you in part 2.